Good day, class. Once more, you're welcome to our organic chemistry lesson. Today, we'll be looking at methyl benzene. Alkyl benzene constitutes of one or more alkyl groups attached to the benzene ring. Alkyl benzene consists of one or more alkyl groups attached to the benzene ring. The simplest alkyl benzene is, as such, it is methyl benzene, which we are going to be looking at today. And that is the structure of methyl benzene. Methyl benzene is otherwise known as toluene. Now we'll be looking at the preparation or synthesis of methyl benzene. Methyl benzene is being prepared solely by alkylation of benzene, that is, using the Friedel-Crafts method. Methyl benzene is prepared by alkylation of benzene using bromomethane and tribromo ion as catalyst, and in the presence of heat, like you can see there. That's the reaction taking place in the presence of heat to give us a methyl benzene, and a byproduct of the reaction is hydrogen bromide and tribromo ion, which is an acid catalyst, and it acts there as a catalyst. We'll be looking at next the reactions of methyl benzene. Methyl benzene undergoes two distinctive types of reactions. That is side chain substitution reactions, which proceed by free radical mechanism, and electrophilic substitution of the ring takes place mostly at 2 or 4 positions of the ring. The first reaction type we'll be looking at is the side chain substitution reactions. And the first side chain substitution reaction is halogenation. The halogens, chlorine and bromine, react with boiling toluene. I told you earlier, toluene is otherwise known as methyl benzene. React with boiling toluene in the presence of ultraviolet light to yield mono, di, and tri-substituted products. Like you can see there, you say it yields mono, di, and tri-substituted products. We have chlorine reacting with methyl benzene in the presence of UV light and is boiled to give us chloromethylbenzene and hydrogen chloride. The next, chloromethylbenzene, is going to yield, reacting with more chlorine, is going to yield as such dichloromethylbenzene. Now, we'll be looking at the next reaction there, where we have dichloromethylbenzene reacting with more chlorine in the presence of UV light to yield us another substituted compound. The side chain substitution, that is the side chain substituted methylbenzene, undergoes hydrolysis to yield alcohol, aldehyde, and carboxylic acid. Like you can see, we say it undergoes hydrolysis to yield alcohol, aldehyde, and carboxylic acid. For example, we have dichloromethylbenzene undergoing hydrolysis, that is reacting with water to yield us benzaldehyde, which is an aldehyde. We also have trichloromethylbenzene reacting with water, that is undergoing hydrolysis to yield us benzoic acid. The next reaction is oxidation reactions. Strong oxidizing agents. We say strong oxidizing agents like potassium permanganate and concentrated nitric acid oxidize the side chain methyl group or any alkyl group from benzene to yield carboxylic acid. I can see that's a reaction there. It's going to yield us carboxylic acid. Methylbenzene undergoing oxidation reaction. It's been oxidized by strong oxidizing reagents to yield a benzoic acid. And the next one there is ethylbenzene in the presence of potassium permanganate and concentrated nitric acid to yield us benzoic acid as well. So you can see these are the various examples, and you see that you also see that if the methyl group or alkyl group attached on the benzene group is more than one, for example, like you can see on your screen, we have it is a di-substituted benzene ring there, where two methyl groups are attached on the benzene ring, one on the first carbon of benzene and the other on the fourth carbon of benzene. It's going to yield us a dibenzoic acid. That is benzene 1,4-dioic acid or 1,4-benzoic acid, and the compound reacting there in the presence of potassium permanganate and concentrated nitric acid is 1,4-methylbenzene, dimethylbenzene, 1,4-dimethylbenzene. The next reaction there is addition reactions of toluene. Toluene can be hydrogenated at 150 degrees Celsius using nickel as the catalyst. Like you can see there, that's nickel as a catalyst to give us methyl cyclohexane. That is methylbenzene undergoing hydrogenation. That's reaction with hydrogen in the presence of nickel catalyst at 150 degrees Celsius is going to yield us methyl cyclohexane. The next reaction there is ring substitution reactions of methylbenzene. The first ring substitution reaction of methylbenzene will be halogens, that is halogenation. Halogens can be substituted in the ring in the presence of suitable halogen carriers and in the dark. Remember that in the presence of light, the benzene ring is going to undergo addition reaction to yield cyclohexane or that is going to yield us fluorinated cyclohexane. But in the presence of dark and acid catalyst, is going to yield us a cyclomethylbenzene, that is a chloromethylbenzene, depending on the carbon atom on which it is attached. Like the example there, we see methylbenzene reacting with chlorine in darkness, and our acid catalyst, aluminum trichloride, is going to yield us 2-chloromethylbenzene or 4-chloromethylbenzene and hydrochloric acid. The next reaction there will be the reaction with concentrated sulfuric acid. Methylbenzene reacts with concentrated sulfuric acid to yield methyl sulfonic acid. Like you can see there, it's going to yield us 2 or 4 methylbenzene sulfonic acid. The next will be the reactions. That is the reaction of methylbenzene with nitrating mixture. Methylbenzene reacts with nitrating mixture to produce methyl nitrobenzene. Like you can see the reaction there. Remember, a nitrating mixture is a mixture of concentrated sulfuric acid and nitric acid. And there, methylbenzene reacts with a nitrating mixture to yield methyl 2 or 4 nitrobenzene. It's going to yield methyl 2 nitrobenzene or methyl 4-nitrobenzene, depending on the carbon atom on which the nitro group is being attached. And we see that in excess nitrating mixture, 2,4,6-trinitromethylbenzene, which is TNT, or trinitrotoluene, is produced. As you can see the excess nitrating mixture, benzene, the presence of excess nitrating mixture react to give us 2,4,6-trinitromethylbenzene, or trinitrotoluene, which is otherwise abbreviated as TNT. The next will be alkylation. Toluene reacts with halogenoalkane in the presence of suitable halogen carriers as catalyst. So it reacts with halogenoalkanes in the presence of suitable halogen carriers as catalyst, and also with alkene in the presence of sulfuric acid as catalyst. And you can see the reacting with methylbenzene reacting with chloroethane in the presence of aluminum trichloride as an acid catalyst to yield us, it's going to yield us a 2,4-ethyl methylbenzene. The next reaction there, methylbenzene reacting with an alkene. In this example here, we're going to use ethene as an alkene, as an example of an alkene. The presence of phosphoric acid is going to give us 4-ethyltoluene. And the next reaction there will be acylation. Under acylation, we realize that methylbenzene reacts with acid chloride and acid anhydrides to form substituted methylbenzene. As you can see them, methylbenzene reacting with chloroethanol is going to yield us, that is reacting with ethanoic acid, ethanol, as in this is the spelling of ethanol. That is, this is chloroethanol. Reacting with chloroethanol to give us A. Then to react to chloroethanol to give us 2,4-methylphenylethanol. 2,4-methylphenylethanol. Now you can see there. Going to give us a 2,4-phenylethanol. We also have an example there. Reacting with acid anhydride, for example, it's going to give us a 2,4-phenylethanol again. And the next thing we'll be looking at is substitution in mono-substituted benzene. That's substitution in mono-substituted benzene. As you can see there, as examples of electron withdrawing species. A substituent in a benzene ring may be electron withdrawing, in which case it deactivates the benzene ring. What we mean here is electron withdrawing species deactivate the benzene ring. The electrons are mostly withdrawn from 2 or 4 positions of the benzene ring. The electrons are mostly withdrawn from 2 or 4 positions of the benzene ring, rendering the third position relatively richer in electrons. That is, when electrons are being drawn, that are withdrawn from the 2 and 4 positions of the benzene ring, it renders the third and fifth position relatively richer in electrons. Now you can see from your screen, you see that X, remember X represents an electron withdrawing species. And when this electron withdrawing species attaches on the benzene ring, you realize that it withdraws electrons from the 2 and 4 positions. And as such, it renders the third and fifth positions electron rich. When electron withdrawing substituent is attached to the benzene ring and the mono-substituted benzene undergoes further reaction, that is when the monobenzene ring undergoes a reaction, undergoes further reaction, any substitution, that's any further substitution, takes place mostly at the third or fifth positions of the benzene ring. Some of the electron withdrawing or deactivating substituents are, we have the nitro group, cyanide group, we have ethers, carboxylic acids, and halogens. When any of these substituents is on the benzene ring, any further substitution, that is any further substitution, attaches at the third or fifth positions. Meanwhile, also we'll be looking at some substituents in the benzene ring are electron donating, in which case they activate the benzene ring or enhance electron density of pi system of benzene ring. What we're saying here is, we're just from looking at electron withdrawing species, and we said when electron withdrawing species are attached on the benzene ring, any further substitution will take place at the third or fifth position, because when an electron withdrawing species or deactivating substituent is attached on the benzene ring, it renders the 2 and 4 positions less electrons, that is, it withdraws electrons from the 2 and 4th positions, as such rendering the third and fifth positions electron rich. Now in this case, what we're saying is, when an electron donating species is being attached on the benzene ring, in which case they activate the benzene ring, that is, electron donating species activate the benzene ring or enhances the electron density of the pi system of benzene. In this case, we are going to see that electron donating species will add, that is, will increase electrons, will increase electrons on the 2 and 4 positions, that is, making them electron rich, and as such rendering the third and fifth positions electron deficient. Each electron donating or activating substituent gives its electrons mostly to the 2, that's the second and 4th positions on the benzene ring. Okay, like you can see on your screen there, you see that the third and fifth positions are electron deficient. When an activating substituent or electron donating group is attached to a benzene ring, then further attachment takes place on the second or 4th positions on the benzene ring. Some activating substituents, that is, examples of activating substituents are, you have the amine group, you have the hydroxy group, we have the alkyl group, and so on. Now with this, when you're given a benzene ring which already has a substituent, which already has an attachment to it, a group attached to it, and you said that this monosubstituted benzene undergoes substitution reaction, that is, you're going to see is going to be determined by the kind of group attached to the benzene, that is going to be determined by the monosubstituted benzene. If it is an electron withdrawing species, then further substitution is going to take place at the third and fifth position. But if it is an electron donating substituent, then further substitution will take place at the 2 and 4 positions. Next, we'll be looking at is rules for further substitution in monosubstituted benzene compounds. When the monosubstituted group on the benzene ring is a saturated group, that is, a saturated group is one that contains only single bonds between all atoms. We say when the monosubstituted group on the benzene ring is a saturated group, that is, it contains only single bonds between all atoms. Then, when the monosubstituted benzene undergoes further reaction, further substitution is directed to the 2 and 4 positions, except the halogens. When the monosubstituent, that is when the monosubstituent group on the benzene ring is an unsaturated group, that is contains double or triple bonds between any atoms. Then, when the monosubstituted benzene ring undergoes further reactions, further substitutions are dedicated to the third or fifth positions. Today, we've come to the end of our lesson. And our next lesson, we'll be looking at alcohols, phenols, and ethers. First of which, we'll be looking at alcohols. We'll look at their characteristics, their reactions, their preparations, and so on.